speaker is Maximilian von Wietersheim-Kramsta, talking about KiDS-SBI simulation-based inference of KiDS 1000 cosmic shear.
Thank you very much to the organizers for having me. I'm here to present my work on the simulation-based inference analysis of the most recent weak lensing data from the kilodegree survey. And yeah, I've come from Durham University, where I'm a postdoc, and I've done this work with these lovely collaborators, with Kai-Am Lin and others. And first, let me explain to you why we've done this. So simulation-based inference is sometimes also known in the literature as likelihood-free inference or implicit likelihood inference. And it's a very powerful method that lets you do full uncertainty propagation from all the way to your data to your final parameters given a model, or even if you want to do model testing, you can do that too. In that way, through simulations or other analytical models, you can imbue arbitrary levels of complexity, as long as it's computationally feasible, into your signal and noise. And then your likelihood can take an arbitrary form, so you can go beyond the Gaussian assumption of your likelihood or other such assumptions. And we've shown in previous work that in the case of weak gravitational lensing, where you have often a 12-dimensional posterior, in our case, you can do that with a similar number of model evaluations than you would do in a standard MCMC analysis. So what actually is SBI? So in essence, SBI is, in a way, a rephrasing of Bayesian inference by zooming out. So I'm sure you're all familiar with this equation, Bayes' theorem. And you can, rather than thinking in terms of only posterior and likelihood, you can zoom out and think in terms of a joint probability. So a joint probability space of all parameters and all possible data given a specific model. So here's an example, which you can see here on this graph, where we have a simplified toy model, where we have a one-dimensional datum and a one-dimensional parameter. And our model, in a statistical sense, is fully characterized by this distribution, where for a given parameter theta, we get all possible observable datums. And that distribution essentially tells us our noise model. And then if we move along this domain, we get our signal model. So this is a very simplified idea, but in fact, this allows you to then go more complex than maybe a standard analysis, where you would assume that the variance of this is constant, like in this case, but you could maybe even make the variance parameter dependent and other things. So simulation-based inference has been around in some form for a while. So here you have the example of approximate Bayesian computation, where you learn this distribution, so you learn your posterior. For a given datum that you observe, you slice across this distribution, and then for a given threshold, you characterize the posterior distribution this way. And this allows you to get that complexity in your likelihood and posterior, but it scales a bit poorly with higher dimensions in your model, and also is lossy because you discard all this information in that red part of your parameter space. So with the proliferation of machine learning, what people have started doing is, rather than doing simple thresholds, they do regression with neural density estimators to characterize the full multivariate distribution across the full parameter space. And then for a given observation, so your true observation, you just slice through this and end up getting your posterior in a likelihood-free way. So there is a likelihood, it's just implicit. So there's a lot of different misnomers there going around. All right, so what are we applying it to? So we're applying it to weak lensing data. And you've already heard from some great talks by Daniela and Ben what that is, so I will be very brief. So in essence, we're interested in the correlations of the shapes of galaxies that we observe at distant redshifts, and how these shapes are distorted coherently by the foreground matter that it encounters along the line of sight as it travels to us, to the observer. So here you can see the KiDS map here, right there. And then we measure that with a survey like the kilodegree survey. So a brief introduction to the kilodegree survey. It's a survey done with the VLT survey telescope in Chile, which is a 2.6 meter telescope, covers about 1,000 square degrees, and was observed in 9 bands across the near-infrared and visible spectrum, which means it also has pretty good photometric redshifts. And then we are interested in doing cosmological inference. So here is one of the previous results that were gotten from KiDS, from Asghari et al., where we see the banana that we've seen before of sigma 8 versus omega matter, and it has been found that that is in 2 plus sigma tension with the Planck observations. So there's been lots of speculation, what could be causing this, and with simulation-based inference, our scope is to address this by imbuing additional complexity into the model and into the analysis through systematics, while keeping the underlying assumptions similar to the standard KiDS analysis, and see whether systematics could be causing this tension. So this is what we've done. We've created a forward simulation pipeline that takes arbitrary cosmologies at the 2-point level, adds all the relevant systematics, so baryon feedback, intrinsic alignments, and then generates fields of lognormal random matter fields that we then populate with galaxies in a way that many of the survey systematics and observational systematics and physical systematics that are considered, and typically not either, are added to the data, and then we measure them many times, populating our multivariate space to fully characterize the model in a statistical sense. So we start by harnessing a drawback from photometric surveys. So as you might know, photometric surveys have uncertainties on their redshifts, and that means that often we do tomography, which means we have a limited resolution along line of sight for these 5 bins, that then for each one we get a redshift distribution that characterizes our redshift uncertainty. But for the simulations, we can harness that as an advantage by saying, well, we can then therefore work at a limited resolution along the line of sight, which means we can work in 2D projection space for our simulations rather than in 3D space. And this is how that looks. So we simulate many, many concentric shells that have coherently sampled matter fields that are correlated with each other according to the correct power spectrum, but do not have any resolution along the line of sight beyond the shell limit. And this allows us then to essentially, at the level of each shell, add also systematics such as intrinsic alignments and baryon feedback. To do that, we actually need to solve an interesting problem, which was the fact that you can no longer get away with the common the common limber approximation used in weak lensing, because in that limit, the correlations between non-overlapping shells actually vanish. And that is about a 10% effect if you do so, so it wouldn't allow us to do percent level inference for weak lensing. So we created a fast integrator of Bessel functions that allows us to do that very quickly, so we can get many, many cosmologies very quickly. Then we project our power spectrum and sample matter fields from that, and then also calculate the convergence along the line of sight for all these matter fields to actually obtain the lensing. Now, once we've done characterized the physical processes, we need to start characterizing the observational systematics. So this happens in part when we sample galaxies within our universe, our simulated universe. So we, of course, consider the realistic KiDS footprint as we sample galaxies. But we also consider the fact that our selection function in KiDS is not isotropic. So there are variations across the whole footprint that make it mean that the probability of observing a galaxy is actually dependent on where you look in the sky, independent of cosmology, due to things like seeing, zodiacal light, and other systematics that occur in the observations. And in fact, that also varies differently for each tomographic bin sample. So we take all of that into account. At the same time, not only is the selection function anisotropic in the angular direction, it's also anisotropic in the line of sight direction. So our redshift distributions, which I've shown you earlier, are not actually homogeneous for a given tomographic bin. They vary depending on where you look. And here in this color bar, you can see the depth parameter I was showing on the map before, where low values mean we have very good observations, and high values in red mean we have poor observations. And you can see here from the residuals that the mean of those redshift distribution shifts. And for the experts in the room, that means our cosmology might shift too. So here you can see the effect of this. So you can see here, this blue line shows you the added power in the correlation function due to variable depth in the simulations. And in orange, you have a theoretical prediction for that. And it's about at the 1% level. And you can also see that this is quite constant across scales, because we have the large-scale variations that we saw in the larger map. But when you zoom in on this, say, 5-degree patch, you can see that there's also smaller patterns, for example, due to the telescope dithering. Now, this is in terms of the galaxy positions and redshifts, but we are interested in shapes as well. And as has already been explained, we measure convergence and shear to characterize that and get the cosmology dependence. And we find that our depth map, which we've shown before, actually correlates with the intrinsic shape of our galaxies as well. So the KiDS sample tends to select certain galaxy shapes more preferentially depending on the observational conditions. So we add that correlation into our simulations as well. Not only that, we also have the fact that our point spread function, which is calibrated from simulations in the kilodegree survey, actually also has some additional uncertainty in the calibration. So this is per tomographic bin. There are about 5 parameters. So we introduce all of these parameters as well in our forward simulation and stochastically vary them to consider that uncertainty as well. And not only are those stochastic, they're also, again, anisotropic and correlated with the previous maps. So we add this additional variation where our residuals from our point spread function model are also folded into the forward simulations such that they are consistent with the real data. And then we essentially measure the data from the forward simulations as we would do from a standard catalog that we got from the telescope, as if we hadn't done anything different. And then we get measurements like these, which we find are broadly consistent. So you can see here, this is for the best fit cosmology, broadly consistent with the real data and also with the analytical modeling one would typically do. And as an added perk, we managed to do all of that with about an order of magnitude less time per evaluation than typical codes that we would run for this about 2 years ago, and actually while still adding more phenomena and gaining accuracy. So that allowed us to actually get to the order of 10 to the 4 simulations within about a day or two of running these simulations and quickly characterize this full likelihood space. So this is how we actually do that. So we got to this point right now where we have our observations. We compress these further using score compression, and then we characterize our distribution. And the nice thing, since these simulations are very quick, we can actually identify interesting parts of parameter space at this stage and actively sample more from our simulations such that our run converges much quicker and we need fewer simulations. So this is the parameters we vary about. We have our 5 Lambda CDM parameters. We have the intrinsic alignment parameter, the baryon feedback parameter, and some additional nuisance parameters. The score compression, we essentially recast our data vector to a data space linearly that is of the same size as our parameter space, and I can explain that further later if you want. And then we fully characterize this likelihood in the multivariate space using neural likelihood estimation with Delphi, where essentially you can think of it as many multivariate Gaussians being fit all at once to reproduce that distribution that we see in the forward simulations. So it's essentially a regression scheme. We test that extensively. We find that our learned distribution is unbiased with respect to our simulations. And we also find that the real data of KiDS is a very likely realization from our forward model. And then we test that with a mock analysis, of course. So we compare a standard Gaussian analysis, an SBI, where we force the likelihood to be Gaussian, and we also do the full SBI, and I'll show you that now. So we find that overall, they all agree very well. So we see that the full SBI and recovers the parameters as expected, but interestingly, it is broader than the standard analysis where we assume a Gaussian. And this is it's also broader in the case where we assume a parameter-dependent Gaussian likelihood. And we find that this turns out that our SBI has picked up a parameter-dependent uncertainty, in other words, cosmic variance. So here you can see how some of the uncertainties on some of the parameters scale with S8. And this is essentially that the simulations have learned that the more clustering there is in the universe, the more cosmic variance there is as well. So this essentially means that by not considering that phenomenon, standard analyses are underrepresenting the uncertainties by about 10%. But now actually getting to the systematics. So I've talked a lot about this anisotropic selection functions and PSF variations. So what do they actually do to our inference? So in orange, I'm going to show a standard analysis where we neglect that and keep everything the same to a standard analysis, but do SBI. And in blue, I'm going to show what happens when you start considering all of these effects. And you end up finding that, as was pointed out in a question earlier, these systematics actually, when considered and modeled for in the inference, push your S8 down by about 5%, meaning that you actually go further away from Planck. But at the same time, as I've already mentioned, your uncertainties increase a little bit, so the degree of tension stays roughly the same. So this is what it looks like. We find broad consistence with previous KiDS results, and find that our model is self-consistent, but also that we have about a 2.9 sigma tension with Planck still. So I will conclude here. We found that we can essentially do a rigorous full SBI of real data and get contours which are in agreement with previous results when we make the same assumptions, but add new information that couldn't be done with a standard analysis when we do the SBI. We find a new measurement of S8 that tells us that we are robust against these systematics that we included in like the anisotropic selection. And we find that neglecting those can bias you by 5%. And we also find that the uncertainty can also be overestimated, at least at the 2-point level. So for future surveys, that means that considering these systematics as we enter the regime of being systematics dominated and no longer noise dominated might be important, and methods like simulation-based inference could be a way to address that. Thank you very much.
Any questions?
Yeah, thank you for your nice presentation. I would like to know, you said that you use an anisotropic model to perform your recipe. And so I would like to know which kind of cosmological parameter you can constrain with this anisotropic model?
So in terms of, we consider standard Lambda CDM, where we assume homogeneity and isotropy at the cosmological level. So that doesn't change. The anisotropy is added at the observational level, where we only essentially consider that our selection function is no longer isotropic. So depending on where you look, the probability of observing a galaxy at a certain redshift and with a given shape varies. So we still infer the same cosmology as a standard analysis would. We just consider that additional selection function.
It's a kind of FLRW perturbation.
Yeah, so it's standard FLRW with a linear perturbation theory added to it to get the lensing potential, yes. So the standard Poisson equation.
Thank you.
Other questions?
Thanks for the talk. I have a question about the compression. So for that, you have to assume a likelihood, right?
That's correct.
The whole idea here
Yes.
is not to assume any likelihood.
No, that's a very good question.
So is that risky for future applications, or you think it's roughly okay?
So for future so to first answer your first question about the likelihood. So in principle, it seems risky, but you can actually prove that it's not. So score compression is actually a universal compression that does not destroy non-Gaussian information if it's there. Because as you can see here, you are actually expanding about the maximum of your likelihood, meaning that if your likelihood is peaked around that point, all the other terms should be negligent. So as long as your likelihood is peaked and your fiducial cosmology is at that point, you are not actually doing a bad compression and destroying any information. We actually harden against this further by actually testing this. So where we artificially say our fiducial cosmology is now really bad from the true cosmology, and see if that biases our inference. And it actually doesn't. In fact, it's been shown from score compression in many contexts that if you assume the wrong likelihood or the wrong cosmology, you end up just being suboptimal in your compression, but not biased. So we actually have I think there's another where here we actually sampled from a Wishart distribution while telling it is a Gaussian, and it also made no effect. And to further mitigate this, despite us knowing that the likelihood turns out to be roughly Gaussian in the actual data, we do an iterative approach where we run the whole pipeline once and then recompress, using the best fit cosmology as the fiducial of the second round of compression to make sure we don't do anything wrong. Turns out it makes virtually no difference. So that's how you can improve it. As to your other question about future applications, so we wanted to keep it to the lowest common denominator where everything is understandable. And score compression is linear and model dependent and physical. So it was an understandable way of compressing. But for future surveys or future applications, it is certainly possible to use more complicated ways of compression, like neural compression, that are more agnostic to the likelihood. But we just wanted to keep it explainable.
Last question.
Great talk, Max. Could you go to your plot with the S8 estimates from the different surveys? Yeah, so I was looking at this and noticed that the isotropic systematics model has quite asymmetric error bars relative to like the anisotropic systematics model. And I was wondering why that is, or do you have any insight into that?
So partially that seems to be the case that due to the uncertainty dependence in the model, we actually, from the variance we measure from the data, we get constraints on S8 as well, because our variance is also, we find, is uncertainty dependent. And since the neglecting of these systematics adds power to your S8, as was already mentioned, you end up being pushed to a regime in S8 where the cosmic variance actually disfavors even higher S8. At least that's our interpretation of it.
So let's thank the speaker again.